Here are solutions to homework set number 7 for ECE 111, Introduction to ECE. This homework set looks at using Matlab to do numerical integration for functions. So starting out, what we'll do is use Matlab to calculate the integral of a function using numerical methods. The advantage of that is if I can get the function into Matlab, like the blue curve, I can use Matlab to integrate it. Now Matlab won't tell you what the function is, but it'll tell you that whatever the integral is, it looks like the red line. Second thing we'll do, with integration, you can do animation. For example, this is a bouncing ball simulation. I've got a ball bouncing around the screen. When I hit the right wall, I bounce left. When I hit the bottom, I bounce up. Hit the left side, I bounce over. Finally, we'll look at using integration to simulate launching a tennis ball. To launch a tennis ball at a certain angle, certain velocity, I can use numerical integration to calculate the path the tennis ball will fly at. Then the goal is to come up with the initial velocity and angle to hit a target. Now the first problem isn't really a Matlab problem, it's just conceptual. Sketched by hand, if here's the function y of t, what is the integral of y? And assume initially the value is at -4. Integration is area under the curve. Think about this like your checking account. If I start out with -$4 in my bank account, the bank is really good. It will remember that you still have -$4 if you do nothing. So I just keep on going at -4. If I add money, the balance goes up. The amount I add is the area under the curve. So here's the triangle. Area is 1/2 base times height. So I add a half. So I take -4, go up by half. I now add about 3. Ish. So it'll be 1/2 base times height. That's 1.51. 2.5. So we go up 2.5, 1, 2 to here. I now add +4. So we'll go up 4, 1, 2, 3, 4. I go up 3.5, 1, 2, 3.5. Oh, let's see, half base times height, that's 1.5 times a half. 3/8, just a little bit more. Then I start coming down. So here's -2, -3. 1, 2, 3. Come down 4. 1, 2, 3, 4. Come down 2. And then 0. So that's really all integration is. It's adding the area. When the function is positive, I go up. When it's negative, I go down. Kind of like money in your checking account. When I add money, my balance goes up. When I take money out, it goes down. And at the end, I'm left with an integration constant. Integral 0 is a constant. Problem number 2. Find the integral of this function. Now, when you take Calculus 2, you'll learn how to find the integral by hand. Here, we're just going to use numerical methods in Matlab. That's part of the power of Matlab. If I can get the function into Matlab, I can find the integral. And the approach I'm going to use is trapezoid rule. So if I have a function like this, and it's sampled, in this case, every 0.01 second, the area at this point I is the previous area plus the area of this section. Now, one way to approximate that is the trapezoid rule. Just take y of I minus 1, y of I, take the average of the two times the width. That's the area of the trapezoid. So here's the average height times the width is this area, add to the previous area, and spin through all the data. That's called numerical integration. What that means is once I have that function in Matlab, I can use it. So I'll input my function x. So x goes from -10 to +10. Y is cosine of 3x divided by 1 plus x squared. You've got to use that dot notation to tell Matlab, don't treat this like a matrix. Treat that as 2,000 separate numbers. Then compute the integral and then plot it. So here's what it looks like. Here is y. Here is the integral of y. That's part of the power of Matlab. I don't know what the equation is for that function, but whatever it is, that's what the integral looks like. Try that for another function. I have two sine waves, throw that into Matlab, find the integral using numerical methods. So here's y, here's the integral of y. And kind of notice that integration is different than differentiation. Differentiation amplified the high frequency term. Integration smooths it out. That's one of the reasons we like integration in engineering. Integration cleans up your signal, gets rid of the high frequency terms. So given a choice of integration and differentiation, you always want to integrate. Integration cleans up the signal. Differentiation amplifies the noise. Problem number 4 looks at doing a bouncing ball. So suppose I launch a tennis ball on the moon. Here's the acceleration due to gravity on the moon. At this initial condition, there's x and y at t equals 0, the initial velocity in the x direction, initial velocity in the y direction. Where's the ball going to go? Well, what I can do is use numerical integration. Here's the acceleration. Integrate once, I get velocity. And here I'm using Euler integration. It's simple, not the best form of integration, but simple. I like simple. Integrate again and get position, and plot it. So when I do that, here's what it looks like. So there's the position of the ball. Now notice that Matlab is not designed for animation, but Matlab actually does a really good job at animation. I'll stop on the second hit, and poof, there it is. Now what that did is that tells me that the second bounce is at 8.06. If I want the second bounce to be at 10, what I can do is just scale it. So let's see. This velocity gave me 8.06. If I scale it, I should land at 10. So let's try it. So I'm going to run this program, speed up a little bit in the x direction. Here it comes down. Here's the first bounce. And the second bounce. If you type in hold on, that's what's on the solutions. That just saves the position. And I actually hit at 10.000. That's the bouncing ball. The last one is a shoot game. Go to Bison Academy, copy the program called shoot, and then save it in your current directory. I can now call it. I can't execute it. If I try to execute it, I get an error statement. So where's Matlab? There's Matlab saying you can't execute subroutines. You can call them, but you can't execute them. Pick a random target. Here's my initial speed, initial angle, target. Let's say it's at 92 meters. I'm going to launch a tennis ball. There it is. And what that tells me is that I missed the target by 17 meters. Try to hit the target. So what I could do is 30 was too short. Let's try 40 meters per second. I launch a tennis ball. It goes out. What the shoot game is doing is using numerical integration. I know the acceleration at any given time. That's due to gravity pulling down. Ball's got wind drag. Integrate acceleration once, I get velocity. Integrate twice, I get position. Plot the position. Then repeat every 10 milliseconds. So that was long. My next guess would be like 35. And if you guess again, guess again. Eventually you can get there. That's problem 6. The last problem is there's a better way than guessing. What I could do is use Newton's method or California method. If I try California method, what this will do is, suppose my target's at 92. I'm going to take my first guess. I'm going to shoot at 30 meters per second. Well, I know 0 is going to give me 0. Next guess is at 30 meters per second. And the first guess, I'm going to miss the target by 92 meters. What's my next guess? This is California method. I can interpolate and basically find the zero crossing if I extrapolate the first point from the second one. So 0 gives me 0. That's 30. The next guess, go over to Matlab, is 36 meters per second. That missed by 16. Long. And interpolate, next guess is 33.61. Missed by a short, 0.37 meters. Next guess is 33.69. Just about nailed it. And third iteration, I hit the target. So that's numerical integration. If I can specify the acceleration, I can integrate and get velocity. Integrate again, I get position. Integration is kind of useful. With that, I can find the integral functions. I can do animation. And when you get to animation, if I want to hit a target and I'll launch a tennis ball game, there are ways to do it other than guessing. Newton's method, California method work really, really well. And that is homework set number 7 for ECE 111.